Okay, it looks like we are live. So welcome back. Today I'm going to be continuing to work on my virtual machine. So, today, I'm going to do more work with the registers as well as floating point numbers. So, I merged the register branch. I think I'm going to keep them. I think they could have some good uses. But first of all, I want to work on printing floating point numbers because we don't have any support for that in the slightest. So in test.tasm, I can delete all this. So I want to be able to push a floating point number, so just any floating point number, 4.20 for example, and then just call print float or something like that, and then print it essentially. We do have support for that with integers. Well, so we have a few different ways to do that. We have one that is written in the actual assembly. I can show here. So int. No, it's print int it's actually dot tasm or dot tash rather, because it's like a header file. I just can call it and then it will print an integer. So I can show that with the print int example. Oh, whoops! I need to actually compile everything. Yeah, so if I run that and then run that, you can see it prints that integer. So that's cool, but we don't have support for that. So to do that, I think we're going to need the actual print int as well, because we're going to have to print it. So I think I'll implement it as a native function first, like the float to stir, like how we have the int to stir. So right here, yeah, we have this. So I will just sort of copy that and then make int float to stir, and it'll take all the same stuff, stir index, and then also it will take a float, so a double x. So we can actually call int to stir to get the first part. So if we basically need to basically append to the string all of this. So if we call this, we can call int to stir, and we pass in the stir as well as the stir index, and then we cast this to an int64t x, just like that. Then I think that will help us a bit, and then I can just print this to show what happens, sort of. So if I print the stir now, yeah, so that should print the first part of it. So yeah, so let me add this, let me add this to the natives. Let's see, native functions. All right, so it's actually down towards the bottom. Right here. So where do we have? Let's see. Yeah, so this one. So I will actually. I'll make it 98. So we have into ASCII, and then we need float to ASCII. Yeah, it'll be 98. So I can add that to the standard defs as well. Into stir, yeah, and then just right up here we can have float to stir and make this 98, just like that. And then yeah, okay. Then we'll be able to use it, but yeah, so let me open test.tasm. So I will do that, and then I will call float to stir, which is actually native 98 because I'm not importing this any defs right now. So that should print it, assuming I did everything correctly. And I did not. So yeah, I didn't actually implement it. So into ASCII, if we go to this, yeah, we basically need to just copy this. So let me copy that there and put it before, actually, because it's defined before. Which maybe it shouldn't be, but all right. So let me make this float to ASCII. And yeah, so we got that, and then yeah, we can call float to stir like that. Yeah, and that should be pretty good. Except this, we want to pop it as a double, so as float, much like that, and then yeah, then we can start with that. So let me not push it or anything. Yeah, so we do need to set the string index. Yeah, well, let's just so let's see what happens now. So it should compile now. Control, oh yeah, so I need to actually return it. So return stir, just like that. So yeah, so this isn't going to, so I need to set stir index equal to that so that we can actually print it. And then so it's supposed to return an integer. So why is that? Is that just, all right, so that's just indicating success, I suppose. So all right, so if we build that, and we need to dereference this. And there we go. So let's compile it. And let's run it, and it prints out 4. So that is what we would want in this case. And then if we make it negative, then it should print out 4. Okay, we want it to print out negative 4 though. So that's not great. Yeah, I guess we have to check if it's negative. Can we not cast it? Let me just let me dupe and then print and see what it says. Yeah, so that is supported. Negative, and it doesn't support it here. So when we cast it, it breaks. Let me print it as a casted number. So for T and X and see what it says. So let me build that and then run it again. And it is negative 4. And when we pass it in here, it doesn't want to do this. So yeah, I'm not sure why it would do that. Let me print it up here as well. But just like that. Build that. Yeah, and it's negative 4 in there. Does it not ever call this? So, yeah, it does. But when we return it, it does not work. So why is that? Let me do that. Yeah, that doesn't work, so that's not. So why doesn't it want to do that? If we do this before doing that, then it's gonna break stuff, right? Yeah, then it does weird stuff. So, are we not iterating it properly? Because it does work with the integers when we do this. Well, then it works. Okay. So, is that something that I forgot to do? Okay. Well, now it works at least. So that's good. Let me make sure. We'll run it one more time. Yeah, so we still print it like that. Whoops. There we go. Alright, and so let me try it on the native 99 and do this with just 4, like that. And negative 4, actually. And make sure it still all works. We'll recompile it, and then we'll run it, and okay. Doesn't do anything now. Ooh, because we're not actually printing it. So, yeah. So we need, so then it's on the stack, so we can push 1 and write, and that should work. Okay, because write doesn't exist, it's native 1. There we go. So if we run that, and then run that, there we go, negative 4. So that is good. So, now we need to do the other half of it, which is a bit more complicated. So, I was actually looking, print float in, or actually convert float to string. Yeah, so that is something that I wanted. And I found this implementation of it right here, and we might be able to use it. So I didn't actually try it out and see if it works. Here we have reverse. So does that reverse the string? Okay, reverses a string of that length. Whoops. So we do have to reverse it here. This is in the int to stir though. So yeah, so this is the implementation. And it calls int to stir, or it calls, yeah, int to stir, their own implementation of it. I think we can use ours for that. So yeah, this is casting it like how we are doing to get the first part. Yeah, so float first part equals n minus I part. Yeah, so let me try that. Let me try this out. So yeah, actually in here, so this is the first part that we're doing. So the stir. So yeah, we just set it to an int. So int to stir. So why does this return an integer? Is that the index? Okay, so return. Okay, so that's like the size, I suppose. Why do we need? Okay. All right. Let me try this. So int to stir. So we can just get the index by doing this, because we're passing it as a pointer, so that should be fine. So I part, Yeah, so that is the, okay, equals int n. So that is sort of what we're doing here. Well, we can do that if we do int, let's just use the same name and try to get something working. So int of x, it's actually int64t, so, and then, and then we can do f part equals n minus float of I part. So that, yeah, so n is actually x, so that would be 4 minus the integer of it, okay, so, yeah, so that's getting the index, so that's when they're calling this on I part, okay, and then, yeah, we're passing this, so that should be fine. Yeah, so that is a bit different, but essentially does the same thing, should, at least, yeah, and then, okay, after point, so what is the after point? So that is where you have to define it. So what does that mean exactly? So is that the decimal places? Okay, so that's what it looks like if after point does not equal 0. So I will figure that out. I'm just trying to get something working right now. So we can actually get that after point. Yeah, I guess after point means the number of decimal places. Then, so stir index is what they're doing there essentially. Yeah, equals dot. Okay, so we add the dot, and then f part equals f part times power. So that is the power of 10 after point. Okay, so I don't know if we have we should have that, but I would like to implement it on my own after. So we call int to stir on that part, the integer of it. So int 64t, like that. There we go. And then this, I don't know that we have to worry about that necessarily, because we're not using that. So we just really need to call it stir index. So actually, what is this? So this is, yeah, so this is actually called wrong. We want to call that on I part rather than x, like that. So yeah, I part, like that. Probably going to change these names. And then this first part, we actually just want to pass the string. And then here, yeah, we need to move this around actually. So we do, whoops, there we go. So we want to pass the string here, and then we want to, oops, I want to move this over here, like that, and then, yeah, get rid of that. Okay, so that should do that. And then what is the last? That looks like it's it. So then we can just set the closing part and then print it. So we'll see what happens now. We don't actually ever actually do that. So that is let me search for it. Native. Let's see. Or it's float to ASCII. There we go. So yeah, we need to pass that to the function. So just a 0. Yeah, and then we'll see what that does. So if we go back up here now, we compile it, and then that is not an integer, so we need to make it an integer. Like this. Dereference it. Okay, and now let's see what happens. So, okay, we're not actually calling the right one. So I need to do that. And that's going to print out on its own. So let's make this 4.0 like that. And it prints out 4. Okay, so it didn't work. Okay. So, oh, because I passed the after point as 0. So let me just do that. There we go. 40. Okay, so that's not good. Because it didn't append the, oh, we need to iterate string index actually. Plus equals 1, something like that. And there we go. Okay, so it did that. So let's make this 4.20 like that, and it should okay, so that is not good. So why did it do that? That is a tad strange. After point, okay. F part. Oh, because that has negative on it. So if it's not negative, does it work properly? It does seem to, so let's see. So we can do 40, so I'll do pi instead. 3.14. There we go, something like that. And let's see. Okay, so that is working. It just doesn't work with negative. If we can fix that, hopefully. Yeah. So we need to, I suppose we can do if f part is less than 0, then we'll do f part equals negative f part. There we go. And then that should be fine. So let's try that. Okay. There we go. So that looks like it worked, actually. That was not too difficult. So, yeah. So it's implemented now in here. Let me do some tests to make sure. So what if we do something like that? We compile it. Okay. And that all looks right. And then, so we can't do any greater than that. So I think, well, if I just set it to 8 by default, yeah. So I could make this a parameter, but I'll probably just set it to 8 as the default, and then I can change it later. Yeah, so we'll just set it to 8. Because it's not like it prints them all, so it's like dependent on how long it is. So if we do something like that, it doesn't print all the way. Oh, I guess it does. Okay. Yeah, well that's okay. That is okay. I think we can live with that. And this should be able to be pretty long. Okay, so it actually did overflow with that. Get rid of some of these. Yeah, okay, so that works. So that is pretty good, I think. And then not negative versus well. Okay, yeah, so that all looks good to me. Ooh. That's not right. That is not right at all. Yeah, so I'm not sure where that came from. Is it an overflow thing? Is it because this number is too long? I don't know what the float limit is, or the double limit. Yeah, because then it works. So I guess that was an overflow thing. I'm gonna say it's that. Yeah, and then we can do that, and it should work. And okay, yep, that looks good. So now we need to actually make it a proper string. So instead of setting it here, let me see. In the implementation, we set that. We don't want to do that. And we can, yeah, we can return 0 because that is just the error code. And then, yeah, we can do this, reallocate it, and then do that, and push the pointer. And that should push it onto the stack. So then we should be able to write with it. So if we push 1 and then -1, it should write the string. Yep, okay, so that looks good. So we don't append a new line by default, obviously, but that is working. So now we have at least some way to print floats. But I would like a native implementation of it, native to the assembly rather than this. So we do have the print int right here, and I think we can use that. So if we just import that, so let me move this. Instead of writing it in here, then I will actually touch test, and we will do print float hash. We'll do TASM, and then I will actually open that print float. Okay, and then we'll set main here for now, and we'll do entry point main, and then we'll import print int.cache, and that will actually import. Does it? It does not. Okay, so yeah, that's fine. So that will import that, and then we should be able to just call it. So if we push 5, and then we call, what is it called? Is it just print int? Okay, call print int, and that should print it, I think. By, I gotta go into text, and then TASM, let's see, so this is called print float. Alright, print float.tim, and 5. Okay, that works. Something we had to do, though, is it does print a new line. And we don't want that, because basically, we can cast it in the level of the assembly. So if we do 5.0, and then we do int2, actually if we do 5.5, and then we do int2, actually, I think it is a native function. No. So what is it called? Int2 float. Yeah. So it's not native. Yeah. Int2 float. Actually it is float to int, rather. And then run that, and it will print 5. So we can do that, and then we just need to get the second half. Yeah, so we need some way to do that. And for now, I'm just going to remove the new line from here, but I will figure out a better solution later. So yeah, we can do that. We don't need a pop in. Okay, yeah, so then that should print it without the new line. And it's not as nice, but we can do that, and then we want to just print the second half. So we essentially want to do the same thing that we did in the function. So what was, it was, let's see, float to ASCII. There we go, right here. This is the implementation of it. So, no, that is not. We need float to stir, and that is essentially what we're copying, except we're going to be printing instead of appending to a string. So, what's a good way to do that? Because this, yeah. So, yeah, we're basically going to be converting this. So this is the first part, which we're doing here. So, print in. Yeah, so that's fine. So we have the first part done. Then we need to get the second part, which actually calls power, which is a math function. I think we can implement that. It shouldn't be too difficult. Should I implement it in here or as like a native function call? I think, I'll just do a native for now. So I'll just do, I can just go right here after scanf, native pow. Okay, yeah, that should be fine. So let me just implement that. So if I search for native, I'll do native scanf, and I'll add it right after that. Void native pow. Like this, and then, yeah, so I'll just pop off the arguments to it. So we have pow, and then it's the, well, then we raise it to the power of, and then the number. So yeah, so let's see, the number will be popped off last. So we'll do pow, int 64t power equals pop machine dot word dot as int. So it'll be an int, and then the number that we're raising to a power. Let's see, is it actually a float in this implementation? No, so that is just, okay. So yeah, it's just an int, and that is the number of points that we need. So we can do that. That is not the right place. Num equals pop machine dot word dot as int. Perhaps I could check like if it's a float or an integer and pass it like that. I don't know if that actually supports floats, the power function. So yeah, we'll just leave it like this for now. So yeah, so that should work. We just sort of want to then push this on the stack. So so result equals that, and then we can just push machine result like that, and that should be fine. Let me build it, make sure, and it is not, because I need, what else do I have to do? Oh yeah, so result word, or actually then we have to provide the type as well. So it's int type. There we go. Okay. So this needs to actually be casted to a word. And there we go. Okay, so that looks like it is all good. So now, yeah, we can use that. I will define it in the standard defs as well. So it went right after the, right after, which one was it? It was scanf, but I don't see that on here. Did I not add that? Yeah, because we had native scanf, and that goes right after free. So, yeah, I guess we can implement that here. Native 7, and then this is pow. Read is native 7, though. So, I put that in the wrong place. Actually, that is not good. Okay, pow is native 8. Okay, let me see what that is all about. So, where is the read? So that should be 2. So why is it down here? That is not right. We can just get rid of that. Yeah, so I guess stuff was broken. 8. Okay, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Alright, so I'm not sure what that's about. But yeah. So now we should have the power function. So let's go back to float to stir. Then we should have everything that we need for this. So this is just the first part, so we're good for that. And then here's the after point. So we'll just have it be 8 by default. We'll just assume it's that. And then, yeah, so we need to actually write a dot like that. Let me close this. So we can actually just do that pretty easily if we just push a character of dot like that, and then we can reference it, and then we can push 1 and call native 1, and that should push a dot. There we go. So dot. So we have that now. Then we just need to do this stuff in here. So we do fpart equals that. So we still have the first part, or no, I guess we don't have it as an integer. So I guess, well, so we can just use the casted version of it. So let me move it to, let's see, move RD0 top, something like that. So that'll be in the register, and then that should be fine. So we should still have it. Let me make sure. All right, register but found label. It's just R0, not RD0. I don't know why. All right. Yeah. So then we should be able to get it from here. So yeah. So we should have that. So we can just push R0, and then we can actually then push. We can push 10 and then push 8. I want to change it actually, I think. So that is the number, that amount after that we'll have. And then we can call power, which is native 8. Bum, bum. And then if it's less than 0, so I won't worry about that for right now. And then we can call that on that. So actually that's not exactly what we want, because we don't have the yeah, so we need to do this actually. So we can actually duplicate this, and then yeah, and then we push let's see, so then we have 5.5. So I suppose we can duplicate that, call that, and then let's see, so on the top we print and then print, then okay, 0, and then so what is the 0? Oh, it's int 5. Okay, and then we have 5.5. So yes, we do have access to it then. So yeah, we'll just duplicate this. And well, actually, do we want to swap first? No, we don't want to swap. So we can in swap 0, I think. And that should put that one, put the 5.5 on the top, and then this will be on the bottom. Because basically we just need to subtract it from that. So want to cast it to a float. So yeah, so we want to now swap so that the integer version is on top, and then we'll do float to int, int to float rather, like that, and then we should have the float version of that. So then we can sub, and then let me print and see what it is. Okay, so it didn't work, it looks like. What if I print again? What else is on the stack? So we have 5 on the stack. So that is actually what we want to have on the stack. But this is not right. So we swap it first. Okay. Then it makes it negative none. So that is not good. And it didn't work. So why is that? Let's print what this actually returns. 5. Okay. So that is what we want. But does it not actually, let me look at the yeah, so it should push as a float type, so that should be fine, and it does pop it off. Yeah. So that should be fine. I don't know why it wouldn't do that. So it's 5.0. We swap it and then sub. Do we need to actually not swap it? Yeah. Well, because now it is treating it as an integer for whatever reason. And that's not exactly what we want. So, because it shouldn't be, because it should be considered a float. So why is it doing that? Oh, because we need to sub f. Yeah, I am. Okay, there we go. And then, okay, 0.5. So that is actually what we want, right? So if we change this to be something like that, Okay, yeah. Perfect. Okay, so we have that then. So let's not print it anymore. And we want to just move the top, so that is this one, into the register. And then, yeah, we can get it from here, push 8 and 10, and then call power. So let's go back to that float to stir function. Yeah, and then we just call it to stir on that. So we do want to cast it, I think. So we can do that. Actually, we need to multiply first. So then let's actually F. Actually, maybe is it no? Yeah, so it is morph. Yeah, morph like that. I think there's an underscore, and then we'll print the result of that. Okay, so that is. I'm not sure what is happening here. Yeah. Well, so that is what we want actually to print that. Yeah, but I don't know what this is all about. Why is the number all messed up like that? Because it wasn't just a moment ago. So when we move it here, actually, oh shoot, did I break everything else? So we print the top and then print the, ooh. Oh yeah, because we need to actually pop it off after it, because we don't want it on the top. There we go. Oh, so that's what I needed to do. And then I can just call, I can call print A on that one. That should be on the top, and then it should print out 5.5. Okay, and if I change this to pi, 3.14159, like that, up to 8 decimal places, it can print it. Okay, that is pretty good. That is pretty good. So I am quite happy with this. Let me rename this to print float. And I'll get rid of that, and I will actually make it a tash function, and then we should be able to call. Actually, let me make sure there's nothing left on the top of the stack. So let me just print. Do that a couple times. So there is a 46. Okay, so there is this left on the stack. 46. Where did that come from? I'm not sure. It must be residue from that. But if we pop it off, then it should be nothing. Because we don't want to leave anything on the stack, because it's just printing it and it consumes whatever you have on the stack. So if we actually make a main here, and then we call print float, and we push whatever we want here, so something like that, 425, and we get rid of the push from there, and then we make entry point main, and it should print what we put there. Okay. Ooh. So it didn't work. Oh, because I never actually returned. And there we go. Okay, so prints it out. And yeah, we can make this up to 8. And that is too many, so yeah, that looks pretty good to me. Negatives are not supported though, so I do need to do that. Yeah, because it does that same thing that it was doing before. So I think, let's see, where do we have to check that actually? So that is stir right here is where we are looking at that. So that is right before we call the last one here, right before the power. So it's after the power. So now we need to check. Right here, we'll do push 0 and then compare greater. That is what we want, yes. And then if it's not greater, then we want to just jump to the end like that. And maybe that's not a good labeling exactly. Let's see, so not neg, like that. And then, yeah, so if it's not otherwise, we want to push a negative sign. Or no, we want to actually, no, we just want to push, we want to dupe, I suppose. I want to pop and then dupe. Yeah, we want to pop here as well. So, yeah, pop and then duplicate it. So we should have 2 of the number, and then we just want to subtract it, I think. Sub f, like that. No, it is an integer, right? So, okay, so we can do that, and then, okay, so it didn't quite work. Oh, because we don't want to pop here. Okay, so, yeah, we need to, we only want to pop 1 time. And if you do it twice, it messes it up. So, we could just add an extra jump to go past it. Or, hmm. Up and then end neg. Okay, I'm just gonna do that for now. End neg. Alright, and then end neg is not declared. Oh yeah, because there's an underscore. Like that, there we go. And there we go. So 142.0, so that is not right. And make it shorter. Yeah, so it doesn't work. Okay, so, because it's not getting popped off. Okay, what it should be from this. So, okay, 6. So what is the deal with that? Let me print here. And it is a 0, and then we print again. And, okay, and that is -0. Okay, so that's not right at all. And then we have 46 for some reason. Okay, so what is the deal with this? Okay, and then we underflow. So why is there that? Yeah, I don't know what that's about. Let me go here and print, and let me just do something like that. Okay, so yeah, that is the right number. So right here we have it properly. Right here we pop out the 0, right? Yes, okay. So yeah, so that's the right number. But then we don't have it here anymore. So is there something that I am missing here? Print, and make it negative again. So if it's negative, then it doesn't work. But it was working before, so it's just when we check it, it doesn't work anymore. Anything up here? No, not right there. Up here, rather. For that. So yeah, it's just not right at all. So this doesn't work. Work with positive. Dang, I don't know why. I don't know why it would do that. So when it's negative, and if we don't have this at all, then it works. It just prints the, yeah, if I get rid of this entirely, it's like that, yeah, okay, we can get rid of that. So now, yeah, okay, well, so that still works, and then if we make it negative, then it puts a negative sign for both of them. Ooh, but it's not the right number, so, yeah, so it doesn't work when it's negative, for the second part. So where does it actually break? So if we print here, it's the wrong thing, I assume. Yes, okay. Right here. Yeah, so it's broken in there. Force. Yeah. Okay. So, yeah, so it breaks up here, I suppose. So let's go right to there. And it is not right. So, oh, but it is right as a float. So when we move it here, do we have to actually cast it to an int? Did I not do that? Okay. Cast it to an int like that. Okay, and then we have that right there. So that is not what I wanted. Oh. Yeah, so. Yeah, so it's 0 there. Okay. So. Alright. Yeah, let me just print this. Okay. Yeah, so 46 now. So Let me see. Alright, I need to take a quick break. For a minute. Break for 2 minutes, and I will be right back. Yes. Give me a moment. Okay, I'm back. I do apologize for that. So, okay. So, let's see where we are at now. So that is not right. So, we call this, it's 0. So why is it 0 now? So when we move it in here, it is not 0. So is the register broken? Because here is the... It's correct, here. We move it into the register. And then after we pop it off, it should still be there. Yes, okay. And then it is no longer right. So where is that? And if we print it here, yeah, it's just 0. So I think that the register might be broken. Or actually, here we go. Right here, it is that. So that is correct, actually. But then after that, it is not correct. Oh yeah, then it just becomes 0 when we convert it. So the float to int, does that not work? So we cast it to that. That should be fine. Let me print it here. Word. Let's print that. Actually, is it a problem with? No. Okay, is it a problem? Wait, do we want it to be a float though? At this point, actually, I think we do because we're calling this and then we're multiplying f. So we don't need to cast it like that. But then after this, yeah, after this, the float representation is still not right. So that's not good exactly. Because it's just, yeah. So, so this should be raising it to the power. And right up here, it's right. Yeah, right here. That is correct. But then it is not anymore after we do that. So let's actually print it twice here. And then, yeah, so it's still correct right there, but when we call multiply f, it is not. So what if we swap it? Oh, shoot. Yeah, so we need to actually cast this like that. Okay. And then print it. And it should be, okay, because it was actually an integer, so int to float, actually. There we go. And then when we call this, then when we call it, okay, so that is correct. And then now we want to cast it to an integer, or to a float. To an integer, yeah. Alright, now let's try this out. Okay, and let's see. Run that, and okay, so we're still printing stuff, so it's not working there. But if we run this, okay, so it almost worked. Let's see, do we need to pop it again? Oops, yeah, let me actually print and clean and see what we have here. Okay, now it's gone, so that doesn't actually work. So what are we popping up here? It should be the 0. Yep, okay, so a 0 there. And right here, what is on the top of the set? We have the correct number as an integer. So we just need to... Actually, this sub might be wrong. We want to add. I don't remember how you do that. Okay. So, no, we don't want to add. Do we actually want to push 2 and then multiply and then sub? Okay. 208. Okay, there we go. And let me make sure it still works with the positive because we did change some stuff. Okay. There we go. That looks right for me. So we can make this, should be able to make this anything. Anything like that. And there we go. It does do 9. Alright, well that's not a big deal, that's like a rounding thing. Yeah. Maybe that is not a good thing, but works like that. So that looks pretty good to me. I'm quite happy with that. Okay. So yeah, now we can call that, and then it will print it out just like that. So we can actually look at implementation of this. Yeah, so we can get rid of entry name, get rid of this, and then yeah, create touch. Let's see, print float example, and then in there we can entry main like that, and then we can import print float.cache and import standard defs. And then we can make a main here, import 5.0, and then we can print float. And I guess we didn't need the standard defs, but let me try to compile that. Print float example. Whoops. Print float.tag. So that, because we need to actually make that print float.tasm to print float.tag. There we go. Now let's try to run that. And label main is already declared. So where is it declared? So it's not declared in here. Oh, because I didn't say that. There we go. No, that's still not right. Name. It's not defined in there. So in 3, 0, 1, 2, 1, 2, 3. Here. Okay. Yeah. So that is not good. We aren't declaring main anywhere. I make that main. Or push 5.0 print float. I need to call it. Okay. Print float example dot tim actually. And it does print it. So where is the main? Like, why does it think there's main? Is that actually defined in? Ooh, this needs to be print in dot hash. Do we define main in here? We do not. So I don't know why it would do that. So that's not ideal. Whoops. Yeah, so this should be main though, and I don't know why. No, it is print float example dot tasm. Whoops, it's dot dot slash. There we go. Okay. Main is already played, so it's not though. So I don't get what the issue is. Print float. Ooh, okay, I know what the issue is actually. Yeah, I need to move print float, because I actually moved this and then, yeah, so dot tasm to print float dot hash for real this time, and then I'll quit out of this, and there we go. Now it won't be declared. Okay, perfect. And then print float example dot tim, and there we go. So it prints it, and we can type in whatever we want here. And okay. There we go, and it works. So that is pretty cool. It doesn't print a new line, but we can do that pretty easily if we just push a new line, reference it, push one, and then call write. So if we import the standard depths cache like that, there we go. Whoops. Here, float example.tim, and there we go. So yeah, prints a new line. We do need to add this to the print int example as well, because we don't do that here, and I think that's fine. I think that is fine. Reference it, put one, and write. So I'm going to import standard defs dot cache, and then let me make this standard out instead, and let me print int example dot tasm, and then print int example dot tim, and there we go. It prints the int. Make this standard out, and then make sure this one still works. Okay, so that is looking good. So let me just do something like that. There we go. And yeah, it prints it out. So that is perfect. And I think that we can commit this because now we have two different implementations of that. So that is cool. So implemented, let's see. So it is, what? Float to ASCII, in the as a native function, and print float as an assembly function. There we go. So I'll push that. Okay. Doesn't want to load. Is my Wi-Fi internet out? There we go. Okay. Okay. All right, there we go, and it worked. So let me make sure it went through. And perfect. Okay. So now I want to do some more stuff with the registers. So in the Lexer, actually, this will be in the parser. Yeah, check if register. So let's see what we call that. Check if, let's look at, I'm trying to think. So I want a way to get the number for it. And actually, I think that is in the tasm.c where we're going to use that. So right now, this is what we do. I think instead, if we take the text and we just cut off the first letter of it, because right now it's just R, and then we just use the second part as a number, then we should be able to just use that as the index rather than all this stuff. So, so where is that at? So here's the move. So, yeah, so this is what we're doing here. We're just getting register index. Let me change the function. So it should have the type. So head value.text. Let me print that out. Something like that. And then if I compile this now, and actually I will make a test.tasm file, and I will push 5. Actually, I'll just move. Move R05, something like that, just to test it. And then run tasm. There we go. So it prints that out. So we have the text. So we just need to basically remove the first letter of it. I think we can just do char star remove first character. Essentially is what we're going to do here, and we'll take a string. So this could be used for other things as well. So I'm making it a function. So basically we'll return a new string. So I'll do result equals size of r times sterling of string minus 1. Give me 1 character shorter. Yeah. So I think that's what we want to do. And then yeah, so we're going to return the result. And basically what we'll do is let's see, themer professor followed this minute. Thank you, I appreciate that. If I pronounce that wrong, I do apologize. Okay, so yeah, so basically we're going to be setting basically we'll return so yeah, we'll return remove first character of head value.text, and we'll return actually the ASCII of it like this, and that will get, yeah, so that'll get the value of it because it's going to be, yeah. We might need to cast this to a size t as well, since that is what we are meant to be returning here. So that should be all good. And then let's see, so basically we just need to implement it now. So yeah, it should be pretty easy. So we just ignore the first iteration. So we'll do for in I equals 1, while I is less than sterling of stir I++, and maybe I could make int length equals sterling of stir, and then use that for these rather than calling it several times. And then we can do result I. Actually we want to do let's see, so we want to start at 0 because we want the 0th to be that. Equals let's say length minus 1 equals stir I+1, something like that. And I think that should work. We're gonna build this, and alright, so we have some issues. Len is undeclared, so this is length. Okay, and then it builds. So let's see if that works. So let me just print what this returns. So remove first character, and it should just return the index. So let's call that. Okay, and there's extra stuff. So we need to do this equals that. Okay, whoops, I need to rebuild it actually. And then we'll run it again. So that's still not right, because we want, I suppose we'll just do result I equals, how to start programming in C. What resources do you recommend for studying C? Probably using C is the best way to learn C. Oh, yes, hello. Yeah, so basically, I didn't know C, and then I just started writing stuff in C, and basically the only thing that really confused me about it was pointers and memory management. So I'd recommend something on that. So let me see if I can find a resource on that I use. So let me see. Give me a moment. Because I did watch this great video that explained some stuff and helped me figure it out. But yeah, so for the rest of it, you just kind of have to just figure it out. If you already know a programming language, it's not too difficult because most programming languages are based on C. Let me see. Yep, I found it. So I actually pull this up. This is a video that I watched that helped me a lot. So I will put the link in the chat. Right here, there we go. So that video explained about memory allocation, which was what I was quite confused about. That's just an ad. All right. Yeah. So this very helpful video, and I would recommend that. And then otherwise, just sort of mess around programming in C and see what you can figure out. Yeah, so just try to build things. I is undeclared. So actually, let me set this to a lane. Oh, whoops, I need to build it again. Okay, so length -1. Rebuild it. And then run it and see. Okay, so that looks good. Okay, and actually let me then push R0. And then print. Yeah. And so that'll let me see what it is. And okay, 5. So that looks good to me, I think. See if we make this top and we push 69 here like that. Then there we go. Alright, so that I think works. And then so we could change it to anything, even one that doesn't exist right now, like R9. Whoops. Whoops. Oh yeah, because that's actually alright. So that one works actually. Because we can't test it. But it goes up to 3, so it should work. Yeah. So 3 is actually. Thanks for the answer. No problem. Yeah. If you have any other questions, I'm not very good at programming. Just a disclaimer, at C at least. I'm still pretty new to it. But yes, if you have any other questions, I would be happy to answer. Okay. It looks like that works. Yeah, and it actually gets it properly. So now it'll be a lot easier to add new registers. Because yeah, that is, we don't have to do all this stuff that we did in here. So yeah, so we can just return that, and there we go. So what I'm thinking is perhaps actually, let me get rid of that. Let me make sure that there is no other stuff. All right, nothing printing. So that is pretty simple. Let me see. So adding new registers, right now we have to define them in a few different places. It would be nice if a register could just be anything that starts with R and then has a number afterward. And then, well, yeah, then we could just use that, and it could be essentially infinite. We would have like a max register count. But, so rather than doing this, we get rid of that and we just add registers. And then we check the keyword. If it starts with R and then afterward it is an integer, then we just set it automatically to a register type. So let me see if I can implement that. So right now we define these here. So let me just get rid of that and then make this type register. So then it will just be a general register like that. And then here, yeah, we can just get rid of all these, and I'll just make this say register. Yeah, because we aren't actually going to be using that unless we're printing it out. So then in, let's see. So check, let's see. So generate keyword, we have this. So what I want to do is make a new function. Let's see. So token type, yeah, token type. Check if register, or maybe just check register. No, check if register, and it takes the name, and then we'll basically look if name 0 equals R, and name 1 is digit, name 1, something like that. Then we will return type register. Yeah, so then we'll set it there. So here, type equals that. So first we want to check if register. So token type equals check if register. So we do need to keyword name like that. We do need to return type none otherwise. And then we can actually get rid of this. So if it is none, then we'll do that. And then if it's still none after that, we want to check again. So yeah, we're basically just doing the same check again. Right there. Except with this rather than that. So that should work, I think. Yeah, because we want to check if it's a register first, because we don't want to. I guess we could check built-in keywords first. because we don't want it to be set as the label, though. That is quite important that it is not. So let me try compiling that. All right, okay, so now this is because we removed these. So this is in the parser. Parser. So let me just search for that. Type R0 like this. Yeah, so basically just if type register. And then that should be all that we need for this actually. So it might not need to be a function anymore, but there we go. Then we'll return that. So let's look at what we do. Check if register. Okay. And let me actually compile this now. And do we get multiple definition of check if register? Because we call that here as well. Check if register type. That's what we'll call this one. Check if register type. And then that is actually right here. Okay, and we'll build that. And now there's not multiple definitions. And it should still work. Okay, and it did work. I accidentally closed the window. But yeah, so it did work. And now, if we make this 9, it'll still work, but it won't work. Yeah, so it compiles, but then that is not right. We make this 9. Yeah, because that is actually out of the index. So I guess it still works. That is strange. But in the team.h, we actually have this. So we have, yeah, amount of registers right now is 4. So let me just make this something like 32. And then we could have up to 32. So, yeah, so we could have up to register 31, like that. So let me actually make this 32, and then I just want to add a check so that we don't go over this, even though it would, I guess, supposedly work. We don't want it to do that, because it does that. So let me print out what the register name is, actually. Print f. Let's see, add value.text. I want to make sure that, okay, so it is R32, so that is what we wanted. Let me actually print what this returns as well. So, yeah, so I just want to look at the remove first character, add value.text, and I want to make sure it is 32. And it's not setting it to 3 or something. Alright, so it is 32. So that is good. Yeah, so in the tim.c, we just need to basically check if... maybe we could check here. In here, we could do... Yeah, so we could do... size t result equals size t epoi remove first character head value.text, like so. And here we'll just return result, but then we'll check that it is less than. So if result is greater than so it is register. What is it called? Amount of registers. So if it is greater than amount of registers, then we can fprintf error register index is too great. It's too great. Yes, and then exit with 1. And negatives shouldn't be supported anyway because we don't check if it's a negative afterwards. So we do that, and then we run. Alright, so actually it didn't work. Greater than or equal to. Okay, so it still doesn't. Oh, I need to rebuild it. And then if we run this, then there we go. Register index is too great. Yes, that is a good message. And then if it's 1 less, it should be fine. Yes, and then it shouldn't take fault. Oh, right, perfect. So yeah, now we have 32 registers technically, so that is pretty cool. I don't know that we'll need that many, and I can change that anytime very easily by just changing that one number. But yeah, that is pretty nice. So, and we could also make it even more if we wanted. If we wanted, 2,000, could technically do that. Yeah, if I made it like 1000.4, for example, then we could have 1000.3. And that should still work. Okay, I guess it doesn't. Why is that? Oh, because I didn't rebuild it. There we go. Alright, yeah, if we run that, then it should all still work. Yeah, so we have that many now, and if I make it that, it is too great. Yep, alright, so that is pretty cool. I'm not going to do that for now, and I think, yeah, so we'll just do, I'll do 16 for now. So we'll have 16 registers, and I think that should be enough. So, yeah. So that is pretty cool. Pretty cool. Alright, so let me commit this actually. Commit the changes. So let me close out of that and then clear and git agile. Added support for easily adding more registers and also increased register amount to max of 16. There we go, and then I'll push that whenever it decides to load. Alright. And once it goes through, there we go, and okay, perfect. So it looks like it worked fine, went through. So now we have 16 registers that we can use, and I think probably a good use of them would be sort of to prepare calling functions. So basically, functions, they'll take a certain amount of arguments and just set up the registers with the correct arguments that you need initially, and then it takes them from there and puts them on the stack and works with them. I think that is a good use of registers. And then basically the amount of arguments that you can have is the same as the amount of registers. You could also use the stack for it, but then it would get a little messy. Let's see. So let me get clean now. When I see the word TASM, I immediately think of Turbo Assembler from Borland. Alright, well, let's see what that is. That is funny, though. When I think it, I think of The Amazing Spider-Man. Oh, yeah. Turbo Assembler. Wait, is it called TASM? Oh, it is. Okay. I didn't actually know that was a thing already. Yeah, so that's kind of funny, actually. Hi. One accumulating 2 registers with good code generation is hard to do. Okay. So, what do you mean by that exactly? Okay. So, yeah. Small device C compiler. Yeah, so what do you mean, yeah. What do you mean accumulator? I don't know what that means. Yeah. Alright, let's see. Accumulator is, okay. Oh, the register, okay, so in which those are stored. Okay. So what do you mean with good code generation? It's hard to do. I don't quite follow. Ooh, this is actually the example. Alright, well that's pretty cool. Borland once developed an implementation of Object Pascal called Delphi. Based on this assembler. Oh yes, I see actually, Delphi. Yeah. Code optimization. Okay, so 1 accumulator and 2 registers with good code generation is hard to do. So it's hard, you're saying it's hard to optimize with 1 accumulator and 2 registers? Is that what you mean exactly? So this, I think, is what you're talking about, Delphi. Yeah, and that is dialect of Object Pascal. Okay, that's pretty cool. Cool stuff. And so, alright, yeah, well, I didn't know TASM was a thing. Because that is, yeah, because mine is titanium assembly. And it's called TASM. Yeah, I didn't know. I guess I should have looked that up, but kind of funny. I'm not going to change it, but yes. Okay, so we get clean, now we build it, and we make sure everything compiles properly. Okay, and that looks good. So, yes, okay. Yeah, so that's what you meant. Okay. So I apologize, but I don't quite understand like what that has to do with this, because mine has 16 registers right now. That's more than that. Are you saying greater than that makes it harder? Or I just don't quite understand. Yeah, so all those compile. And it all looks like it should still work. Yeah, okay, so I think that is pretty good. Yeah, so let me just build it regular now, and let's see what else we can do. So in the to-do list, string operations don't work. They do now. So that from operations, yeah, so that is something that we could do pretty easily. We're all done with the register, so we don't even need any of the stuff that we finished. Yeah, so this, I think is what I will work on. So right now, all of the operations are popping it off the stack. So if we look at like add, yeah, add. So we can look map operator where it is defined. It's actually in tim.h. So map op, you can see it pops it here. Instead, I think I would rather just set it to the value at the top of the machine. Actually, maybe with that it's just fine. It's more with the let's see, which ones is it? Well, so when we compare it, we do pop them off, and we don't really want to do that. Whereas type. Yeah, so we push that on. So we do want to get. Do we want to get rid of it when we compare? Bum, bum. Alright, let's go to where it's defined. Alright, right here. Yeah, so we push it back on. I think that we don't want to do that. Instead, we'll just get the top of the stack. Because then, if we do this, and we have a pointer to it, then the pointer just becomes invalid. So let me just not do that. And then I'll go to compare. And instead, we'll set this just equal to the top of the stack. Equals machine, stack, machine, stack size, minus 1. And then B can be equal that minus 2. And we have to do minus 1 because the stack size is actually 1 greater. Yeah, so let me make sure it still compiles properly. It does not. Unused parameter B. Oh yeah, so we don't use it anymore. Okay, wait. Ooh, so we only use a.type. Okay. So yeah, we only need to pass a then. So that is fine. So let me go back here. Yeah, so then we just want to do the same thing on all of them. So let's get rid of B. And then, yeah, so I'll just do the same thing for all the compares. Yeah, right here. Right here as well. We have quite a few of these. And I guess I should have tested if it worked before I placed all of them, but unused parameter machine. Oh, so we don't use that either. Okay, so we can get rid of that too, because we just used that. Alright, so let me go down here, and I think I can just query replace it. So compare equal. I just go like this. Then, and I think that's the last one. Yep. Alright, so then I'll just replace let's compare types machine A with compare types A, like that. Dang it, I just completely missed it. Balls. Balls. So I am, okay, let me just do this. There we go. Okay, so let's try that again. So compare types machine A with compare types A. Enter. There we go. Alright, so now let's build it. Alright, and let's make sure it all works. So I'll just make a test.tasm file. Push 5, and then push 5, and then compare equal, and print what is on the top. So I will compile this. And 1. Okay, so that looks good, and if I make this 5.0, it should not work. 0. Have you thought about writing this the other way? How do you mean? Have you thought about writing this the other way? Yeah, I don't quite understand the question. Writing what the other way? Int to float, and if you do that, then it should be equal. Yep. All right. So it looks like it's all working. So that is good. And now it doesn't actually pop off the stack. I don't know if we have any other operations where we would want to do that. So let's just A equals pop. Let's look. So into float, that is fine because we're popping it off. So fine with that because we're converting it. So print. Yeah, print is fine. Move stir. Yeah, that should be fine. Dupe. Yeah, maybe we don't want to pop it off with dupe either. You're currently decoding the instruction and then decoding the subtype. This isn't very performant. The other thing in his case is probably not the fastest dispatch. Okay. So you mean okay, so you mean when we're checking the checking this, let me see. Right here, is this what you're talking about? This function? The compare one? Is this what you mean? I'm not sure exactly. One approach is to write code that writes the code and expand out all cases into very simple operation or ops. If you are doing switches on data types, you are kind of stuck. Actually, I don't even need the switch. If you have to do that at one time. Yeah, well, I'm not trying to write anything optimized right now. But I suppose these correspond with it. So I don't even need to do this. But the actual VM ops shouldn't have too many check-ins. Well, this can literally just be a.data type. Yeah, so obviously this, all right, so this also is not good. Yeah, which I know that. I didn't really, shouldn't have too many check-ins, yeah. Well, I'm just doing it, like, I don't even know if I'm going to keep this. This is just right now for comparing the data types, but, yeah. Because I might get rid of it entirely and then just have different operations, like compare equal, float and int, like that. Yeah. But yeah, so this already does make it a bit better. Just not type. Okay. I misunderstood. You were doing data type compare. Yes. Well, yeah, because basically the point, so we have the different types, which get set by the assembler based on whatever this is. So it can be like that, or it can be like that, or, yeah, or it could just be that. And then it gets set by the assembler, and then it's one of these that we set it to. And then in here, we do compare it like this, based on whatever it is set to. But I did do this now, and I think that is better, because that just converts it, casts it to an integer, since this does correspond with how I was doing it. So, yes. So I did actually make it better, based on what you were saying. And there is probably better ways to do it, but... So is it good now? Or is there something else? Something else that I could do? Oops. Okay. So that. I don't know if your C compiler does tail call optimizations, but you can get a big performance boost from doing function dispatch. Okay. Well, it might do it. Well, so I'm using rather than case. Okay. Rather than a switch case. Okay. It looks like that still works. Okay. So let's look at that. Function dispatch. Which implementation? Okay. So let's look at what you mean by that. Selecting which at runtime. Object oriented. Okay. So like, how would that be implemented in C essentially? Well, so about the tail call optimizations. So I'm using so it's GCC, but it's not like the like I'm not doing that or anything. So it's not the highest version of the optimizer. So I don't know if it goes by default. You can look, I guess. Tail call. I'm not sure if it does. Yeah. So standard C99. Alright, then you can look at that. So that's with O2. Yeah. So I'm assuming it doesn't, like on the least optimized version of it. Yes. Well, also, so this main instruction switch case, it is just more temporary. And then once I have pretty much all the instructions set how I want them, then I'm gonna make a different function for each one and just do basically what I do with the native functions. Which this isn't like I set it this so it's the right numbers, but whoops. But that's probably not this one. Like it could just be like this. But essentially, yeah, it'd be like this. So it's just function pointers. So then Clang, you can switch on just tail. We have big system that uses it. All right, so you can just you can just set it with Clang. Let me look at that actually. Tail call. But yeah, so this I'm going to basically all of them will be called with a function pointer like this, and then this will just be the index essentially of it, the instruction. Yeah. So it wouldn't be using a switch case for the main thing, and that'd probably be faster. I can't spell, I guess, or it just doesn't like the S. Let's see. So you can just switch on with Clang. That's off. Okay. That's LOEM. Yes, I would like to see this. If you have tail call. Yeah, well, I don't. So I'm not sure if it. Yeah, I don't know. I don't know. Then you end each instruction sequence with a call to the next. Okay. I see. And you're just jumping from function to function. Yeah. Okay. Well, so, yeah. So that's not something I'm going to worry about now. Keeping it optimized. Because right now, yeah, this is a bit easier to work with using the switch case. It's pretty clear where everything is and using it and such. But yes, so I will keep that in mind, the optimizations that can be done with it to make it better. Because obviously, I would like it to be as fast as it can be. Yeah, obvious reason. Yeah, so I do appreciate that. Then if you set up the parameters to the functions correctly, the compiler will hold values in real registers, and it screams. Screams? Or do you mean it screams happy? Yeah. Or it actually screams at you, like your computer starts yelling? Okay. Yeah, so that is something that closer to the final version, quote in air quotes, of it. I'll work on implementing something similar to that. Yeah. Goes fast. Oh, okay. Yeah. So I do that in here as well. Actually, the swap function. Yeah, so that we also pop it off. So I don't want to do that. Yeah, so that is something I would like to change as well. So this is actually the string one. So I'll worry about the regular swap first. So A equals machine stack. Yeah. Machine stack size -1. There you go. And then B is -2. Yeah, and then so then we don't want to push it. So we actually want to set a okay, yeah, so we don't want to push it. Then we just want to set machine. We basically want to reverse this. So stack machine stack size -2 equals A, and then -1 equals B. So we're basically setting them equal to each other, like that. Yeah, so I think maybe I want to just set it directly like this. In the system I built, none of the instructions are written by hand. There is code that generates all the instruction sequences, so you can play with register allocation and call sequence. Interesting. Okay, so this. So did you build that for fun, or was it like a work kind of thing? Yeah, so then this can be 2. And then we'll just set it directly, and then not use A at all, and then not push it. And then I do have to make sure that still works, and then I can implement that for the rest of them as well. So just have that, and then we'll swap. I'll make this 4. Okay. So that's not good. Hello there, Buford0014. How are you doing? How are you doing? Yeah, so actually that is not right. Because I want 5 to be on top when I swap it. So I think, actually I just set this to the same one. So, Buford0014 just followed. Thank you, I appreciate it. Alright, yeah, so I was just setting it back to itself. So now let's try that. And then we just have 4 and 4. So that is not good. So, okay, because we need a temporary value of it. Okay, because we're setting it and then we're setting, yeah, okay. So, so let me just do, add scope here. Following immediately because you're as cracked as me. What do you mean, cracked? Like in a good way or a bad thing? Okay, and then I will make a pointer. So word pointer. Let's see. Word pointer. And let's see. So temp equals machine stack size -1. Yeah, so just a pointer to it. So then we can set it. Get the pointer, and then we can set it back. I love doing weird projects in C. Yes, me too. Me too indeed. So then this, I use Linux and NeoVim. Very nice. What distro? What distro? That is very important to add. It's temp, and then so let's see. I think that's still not going to work. Still not going to work because yes. So then we can't set it. I forgot a semicolon too. So we need to. Yeah. Okay. So we can have that. I'm a Debian guy with i3. Nice. Yes, I am using Arch with Awesome Window Manager. Yes, i3 seems very popular among programmers and such. but I've never used it. I'm working on a web browser nowadays in my free time. Nice. Is it open source, and do you have a link or not? Because I would like to check that out. I've always wanted to implement a web browser, and that's something I would like to do at some point. Mostly really just the rendering part of it, like rendering HTML and CSS and such. I think that could be fun. Yeah. Okay, yeah, so this still isn't gonna work. This needs to actually be data. Okay, yeah, I will check that out in a moment. Let me just get this working. Unused variable temp2, okay. Yeah, so we're still setting it equal to that, so that is not what we want. So, yeah, and if we get the pointer to it, it's still not gonna work. So, yeah, because then it's still going to set it the same. So we need to... Yeah. I mean, that works, but it's a duplicate of it, and I didn't want that. I think it's fine. So it is fine. It's fine. So that works now. So we have 5 on the top, and that's what I was expecting. So now let's do index swap. And this will work actually the same way. Right now it does work, but I need it to... I'll just do the same thing essentially. So index... Oops, no, I messed that up. Index swap. Let's look at that. All right, index swap right here. So equals that, and then yeah, so we do push it. So let me grab this. Oops. All right. Yeah. Okay. So yeah. So I basically want to do the same thing, but instead look at the index. And then yeah. So that's basically the same thing that we have here. Equals, yeah, so instead of this we want it to be the top of the machine. So machine stack size -1, like that. And then we don't want to push, so instead we want to then set this top of the machine size -1 equals temp value, like that. So then we get rid of this, build this, and okay, and semicolon undeclared minus, yeah, so this is actually wait, actually what is the issue? Oh, this needs to, no, where, it's right here. So I used a dash instead of an underscore. Okay, and now, and okay, so it works. There we go. So let me actually take a look at this really quick. Browser. I probably won't go too deep into it, but just quickly I want to look at it. So let's see. All right. So let's read through this. So this is, yeah, Buford 0014. Okay, graphical web browser for Linux from scratch. Okay. So, demo, let's look at that. Alright, I'll just watch it here. So I can't see what's being typed. Alright, HTTP, Gemini, Gopher. Alright, installation. Alright, I probably won't compile it right now. I wonder how long it takes to compile. You ever tried to compile Chromium? Takes a while. Yeah, let's look in here. Okay, not too many files. To include. Alright, yeah, so just look at main.c. Okay. Set SSL. Alright, this is switch case on the protocols. Alright, so these just do the same thing. Alright. Pretty cool stuff. Yes. So, how long have you... 28 commits. Okay. Yeah. When was it created? Maybe there's a better way to see that, but September 12th. Okay, so... Alright, and that is pretty cool. Initial release. So is it, there's a release of it, okay. I can actually download. Alright, that is cool. Pretty cool. Currently CLI on. Alright, that is very cool. Very cool stuff. So yeah, the link to it is in the chat. Yeah. Alright, let me get back into this. Sorry, I got distracted. Alright, yeah, so that looks like it works now. Let me push another one. And then we'll swap it again. So I want to print then. So 5 is on the top. Yep. Alright, so that looks like it works. And now let's do index dupe. We want to do the same thing essentially. Index dupe. So yeah, we'll basically just duplicate it. So it's in very early stage. Yes. That is fine. Very cool though, very cool. So actually this is probably fine. Because we're just pushing it. So I think that is fine. Because we do want to make a duplicate of it. So that is good. And I think regular dupe is fine. Let me just check. Inst dupe. No, so we do pop. So instead, we just want to push once. And we'll just set A equal to the machine stack. Machine stack size -1. And then yeah, so we'll just push that. So then it's not a duplicate of it. And let me just make sure it still works. So dupe, and then we should have 3. Okay, perfect. So that seems to work. Perfect. And now, yeah, so I guess I could do the same thing for the string operations. So when we pop the string, it actually is a bit more complicated. Yeah, I think I'll leave that for now. The other operations are fixed though, so that is good. So we do. Alright, X that out. So I'll just move it entirely. So now we have a couple other things in there that I'm not going to work on now. I will push that though. Let's see. Fix the operations to not pop the stack. Alright, push that. Okay, there we go. So hopefully that works a little better now, and I will make sure that works. Okay, and perfect. Alright, so now, I will do a git clean, and then I will build everything, make sure it works, and then, okay, git clean again, because I don't want all that. Build it regular, and let's see what else to do. So actually, let's look in thing.c. So, I've got pretty much everything done that I wanted to do today. Yeah, because now we have the registers. It's much easier to change. We can literally change it here to be any amount that I want. So I could have 6 million registers if I wanted to, and I think that is pretty cool. Yeah, so max string size is that right now. That could probably be larger, but so here's all the registers, and they are stored with the value. Yeah, so I think maybe I can test out some register stuff. So let's push 5. And then let's move R0 top, and then do that for a couple of the registers, okay? And then I will pop, and then there should be nothing on the stack, so I'll just make sure. So I'll compile just in case. There we go. All right, and if I run this, it should stack underflow. All right, so let me just make sure it's stack underflow there. All right, perfect. So now we should have the same value in all 3 registers. It's just a copy of the value, but what's your aim? Will it be QEMU compatible or just a standalone binary? Well, so basically it is here. So I don't know what HDFS is, but basically I'm building a virtual machine like the Java virtual machine. Yeah, so like JVM. So it's for a programming language. Yeah, it's like Java. Yeah. That is, oh, Hadoop. Oh, yes, I see. Okay, yeah, it's going to be like Java. So I am building the virtual machine, and then I have an assembly for it, which compiles to the bytecode. And then I'm going to make a higher level programming language on top of it, like Java, how that works. That compiles to the assembly, which then can be assembled into the bytecode. Yes. So that is the aim for it. And it's really just for fun. But also I want to build some actual projects in it. And the cool thing about it is I can use any C library as well. So because I have native functions, so I can call C functions from the bytecode. So if I wanted to make an OpenGL thing, I could just map the native functions to the OpenGL functions and then actually call them from the program language and then use it. So yeah, I think that's pretty cool. Yeah, and I actually want to build usable stuff in this, and some actual programs. Yeah. So that is the goal, is a program language. A higher level one, rather than the assembly like this. But yeah, so let me then push 0, push R1, and then push R2, and then we should be able to print, and print, and actually let me pop here, and we should have the same value on all three. Okay. So that all works. There we go. Okay, and we can change that. So that is cool, and we can do this as many times as I want. 4, and then yeah, so 3 and 4. There we go, and print, and yeah. So the registers look like they're working, and it can go all the way up to 16. Well, we have 16 total right now. It starts at 0, so it's register 15. And we can store a reference as well, like that. And let's see, I don't think that pops it. So yeah, so that might, let's see what that does actually. It's really cool. I was actually thinking about doing something like this, but gave up after struggling with instruction generation. But maybe I can help. So what were you struggling with the instruction generation? Because that was not too difficult. And I've been having, this is the most fun I've had programming something, pretty much ever. So, character P. Let me, be right. Okay, whoops. Yeah, so that is cool. Yeah, so we can dereference it, and it's no longer on the stack. But we actually have the value that we can dereference. That's pretty cool. But if we change the value on the stack, so then if we push 5 like that, then it should, maybe not. Maybe not. It should be, yeah, I don't know. But, so let's see. So yeah, if we deref, then yeah, so we can dereference all of these if we wanted to. And then, yeah, they all print 8. But it's really just stored as the pointer. So we can move it onto there, the pointer to it. That's pretty cool. So yeah, we can work with pointers pretty easily, and I think the registers help with that. And so I was saying earlier, I was thinking about using these as basically function parameters. So basically you move the arguments into here. So like, say you have add 2 numbers. Essentially is what we're doing. So we'll just have R0 is the first argument, and the R1 is the second, like that. And then you can call add 2 numbers. And before it would use the stack, but this way we can use the registers, and it's a bit easier to see where things are going. So then we would basically push R0 and push R1, and then add, and then return. And then on the top of the stack, well, maybe there could be like an output register, perhaps, where it would basically be set. So then you would basically move, so like R15 or whatever, move R15 top, and then you pop it off the actual stack. Then there won't be anything on the stack. Shouldn't be at least. Add 2, okay, and I spelled that wrong. Numbers. So, whoops. Yeah, so, ooh, that is not good. Alright, should have said stack over, or stack underflow. Ooh, but we don't have entry point name, so oh yeah, feature creep, I know what you mean by that. I am trying not to do that, by sort of limiting some things, like, yeah, but then still leaving, like, it's still possible that it could happen, but it hasn't so far, so, but yeah, so now it does that, and that is good, so that's what I wanted, but now we should have in the R15 register, so if we actually push R15 and then print, then we should get the result. And there we go. So yeah, I think that is a good thing for registers to do, is to be used as function parameters. Yeah, and that's basically the main use of them, parameters, and then I suppose the output as well. And then that's how you could actually return multiple things from it. If we had say 32 registers, 16 are for arguments, and then 16 are for the output. So if you want to return multiple things, then you could just move it into there, that could be interesting. So then basically, yeah, we've moved into there, and then you could have as many, yeah, that could be interesting. Okay, yeah, that's pretty cool, I think indeed. So, yeah, we have that now. We can change this, 15, and then run that, and it's 30. Okay, yes, that is working, and that is pretty cool, and there's nothing else on the stack, so yeah, just, nothing on the stack is used. Those could be cleared as well, I suppose, if you wanted to. Maybe there should be an instruction to basically clear registers or something like that, and it sets them all to 0. That might be a good idea. That could be a good idea. I'll think about that. And yeah, and it also is obviously useful if you're allocating memory, like so you call malloc or whatever, and then, because there is an instruction for that, you call malloc, and then you actually move the pointer into a register to save it. That could be useful as well. Yeah, there's a lot of uses for it. I think it is a good thing that I've added. Yeah, so, so what is something else that I could implement? Because I have string reverse, and that works. Let me actually, so I don't have too much more time. I will have to go soon. But yeah, if you have any ideas, of something that I could try to implement, in the assembly, you can actually look. So basically here's all the stuff that I have right now that I have implemented, at least. So I have all these things. If you have if you have another idea, then I would be happy to hear it, and I could try to implement that. Just like a simple thing to test the language, essentially. Make sure everything works and that it's capable of. Yeah, right now there's no networking or like there's no networking capabilities, or there's no threading or anything like that, because I don't have the native functions for that, but I could do that quite easily. Okay, yeah, let's just kind of see. So I could do like an E calculator. I'm not sure how to do that exactly. Maybe. Let's see. Calculate E and C. Let me just look at a C example of it and see if I could implement that, perhaps. No, E to digit in C. That is what I would like. Yeah. That looks like, okay. Yeah. So, all right. Pretty convenient built-in. Okay, this is Python. I don't want Python. Yeah, so that is a thing. Yeah, I don't know. Maybe I'll do this off stream. I'll probably have to end it now. Yeah, so, yeah, I suppose that is probably about it. Let me just read through this a little. Yeah, these are not very cool stuff. Yeah, so, I'll add some of these off stream, but that is going to be about it for today.